Welcome to the Deep Dive. Today, we're digging into something really important, the story of global ice. Its history, the science behind it, and, well, its future, which seems to be changing faster than we thought.
Yeah, and for this, we're drawing a lot from geophysics research, especially the groundwork laid by Henry Pollack and others who really mapped out Earth temperature history over time.
Okay, so first things first. We need to think about ice differently, right? Not just, winter snow.
Exactly. Ice is this massive geological player. It's shaped landscapes, moved mountains of Earth, and maybe, most importantly, it acts like Earth's thermostat.
A thermostat, I like that. And the scale is just mind-boggling. If you think back, 20,000 years ago?
To 20,000 years, yeah. Places like New York, Chicago, Detroit, huge cities, now they were buried
Buried under how much ice?
under almost a mile of ice. An enormous sheet covering vast areas. It's hard to even picture.
It really is. And that sheer white expanse, that's crucial for the climate, isn't it?
Absolutely crucial. It comes down to a property called albedo, basically how white or reflective something is.
And ice is very reflective.
Fantastically reflective. Snow and ice bounce a lot of sunlight straight back into space. Right now, the Earth reflects about 30% of the sun's energy that hits it.
And ice accounts for a big part of that 30%.
A huge part. That's why the polar regions are so critical. When that ice melts and you expose the darker ocean or land underneath.
It absorbs more heat.
Precisely. More absorption means more warming, which means more melting. It's this positive feedback loop. A bit of a vicious cycle, really.
Okay, so let's track this thermostat back in time. Deep geological time. What does the rock record tell us?
Well, geologists reading that book of rocks found something interesting. Earth's climate history seems pretty binary. It's either been largely ice-free or, like now, kind of half covered in ice at the poles.
And Antarctica's story is particularly dramatic. It wasn't always frozen solid.
Not at all. That's one of the most fascinating parts. Go back 200 million years. Antarctica is part of the supercontinent Gondwanaland,
And where was it located then?
around 40 degrees south latitude. Think similar to the climate of the mainland U.S. today. Temperate.
So green, forests.
Definitely lush forests, actually. We find the proof today is coal beds tucked away in the Transantarctic Mountains, remnants of those ancient forests.
Oh, wow. So it was temperate, part of this big landmass, and then plate tectonics started doing its thing.
Right. The continents started drifting apart, slowly rearranging the map. But the really decisive change for Antarctica happened between 30 and 40 million years ago.
What was that?
Two key things. Australia broke away and drifted north. And then critically, the land connection between South America and the Antarctic Peninsula, the Andean link, it snapped.
Creating the Drake Passage, that gap between South America and Antarctica.
Exactly, a 600-mile wide gap. Seems huge to us, but geologically, it was the key event.
Why was it so important?
Because opening that passage allowed a new ocean current to form, the Antarctic Circumpolar Current, the ACC.
Okay, what does that do?
It's this incredibly powerful ring of cold water that just constantly circles Antarctica, around 60 degrees south. It's the biggest current on Earth, and it acts like a barrier.
A barrier keeping warm water out.
You got it. It effectively isolates Antarctica from the warmer waters further north. It creates this sharp boundary, the Antarctic convergence.
Where the cold polar water meets the warmer temperate water.
Yeah, and they meet, but they don't really mix effectively. Someone described it as a marriage thwarted by frigidity, which I think captures it perfectly.
Huh, yeah. So the current and the winds basically put Antarctica in a deep freeze.
Seal it off climatically. Yeah. And that allowed the huge ice sheets we see today to build up and, well, stay there for millions of years.
Okay, that sets the stage perfectly for when humans start exploring. We jump forward quite a bit to Captain Cook, late 1760s.
Right. Captain James Cook's first big voyage. Officially, his mission was scientific observing the transit of Venus.
But he had secret orders, didn't he?
He did. Secret orders from the British Admiralty to find the Terra Australis Incognita.
The unknown southern land. This idea that there had to be a massive continent in the south.
Yeah, this old idea going back to Aristotle and Ptolemy. They believed the world needed balance, hemispheric symmetry. So a big landmass in the north must mean a big one in the south.
Cook didn't find that giant continent, though.
No, he sailed far enough south to disprove the land symmetry. But he did find a symmetry of ice. He hit this massive, impassable ice barrier in the south, just like the ice barriers explorers were finding in the Arctic.
So icy poles, north and south, that symmetry was real.
It was. And this idea of claiming southern lands didn't die out. Fast forward to the early 20th century, and you see this scramble for Antarctica.
By European powers, Australia, New Zealand.
Exactly. It mirrors the imperialism happening elsewhere. Think about the Berlin Conference in 1884, where European powers carved up Africa.
You're saying the Antarctic claims were like that, just drawing lines on a map, even though it was this incredibly harsh place?
Pretty much. It was about national prestige, potential future resources, controlling southern sea routes, staking a claim, even on ice.
It's fascinating how this era of rivalry, especially later during the Cold War, actually ended up giving us crucial climate data.
It's one of history's great ironies, really. It started, strangely enough, with cooperation in the International Geophysical Year, 1957-58.
Right, IGY. Sputnik went up, Explorer 1, a big year for science.
Huge international effort, shared data centers. But at the same time, the military competition was fierce, especially in the Arctic.
Like the U.S. submarine, the Nautilus, surfacing at the North Pole in '58.
Yes, big power plays showing they could operate under the ice. But while they were there,
They were collecting data?
secretly, yes,
Yeah.
mapping the seabed bathymetry, measuring the ice thickness. Critical geophysical data. And the Soviets?
Doing the same thing.
Pretty much the exact same thing. Both U.S. and Soviet subs were running parallel missions, gathering incredibly detailed data about the Arctic Ocean environment, all classified, of course.
So 2 independent, top-secret data sets covering decades.
From about 1948 right up to 1993, locked away in military archives. Scientists knew this data probably existed, but couldn't touch it.
Until when? When did that change?
The big moment was 1997, the Gore-Chernomyrdin Agreement between the U.S. and Russia.
What did they agree on?
They essentially realized this old Cold War data didn't have much strategic value anymore, so they agreed to declassify it and release it to the international scientific community.
Wow, so that decades-long secret data collection suddenly became the baseline.
Absolutely essential baseline. Without that lucky accident of Cold War paranoia, our understanding of how much Arctic sea ice we've lost recently would be far less certain.
That historical context is amazing, and it leads us right into the evidence for the warming itself. The IPCC, the big international climate body, calls the warming unequivocal.
That's the word they use, unequivocal. Based on direct temperature measurements, melting ice, rising sea levels, multiple lines of evidence all pointing the same way.
And it's not just thermometers, right? There are other natural indicators.
That's what makes the case so strong. We have what are called proxies, nature's own thermometers. They confirm the warming trends independently of our instruments.
Like borehole data? What's that involve?
It sounds basic, but it's powerful. Scientists measure temperatures deep down in rock boreholes across continents. Heat moves very slowly through rock.
So the rock layers hold a memory of past temperatures.
Exactly. And that data shows the Earth's crust has been warming steadily since about 1500. But here's the kicker. About half of that total warming happened just in the 20th century.
Half the warming in the last 100 years of that 500-year period. That's acceleration,
Serious acceleration. Then you have phenology,
which is about timing in nature, like when plants flower or birds migrate.
right? The timing of biological events. There's a great example from the Mohawk Mountain House in New York. They've kept records since 1896.
And what do those show?
The growing season there is now 10 days longer than it was a century ago. And their average annual temperature, up by 2.7 degrees Fahrenheit. Biology confirming the physics.
And what about ice itself? Flake ice?
Another clear signal. Lake Mendota in Wisconsin has ice records going back to 1850.
Don't tell me. Later freezing, earlier thawing.
You guessed it. It freezes about 9 days later now, on average, and the ice breaks up almost 2 weeks earlier in the spring. That's a big change in the lake's seasonal cycle.
But the most visually dramatic evidence has to be the glaciers melting.
Oh, absolutely. Glacier National Park in Montana is the poster child, sadly.
How many glaciers did it used to have?
Back in 1850, around 150. Today, fewer than 30 remain.
Fewer than 30 out of 150. And the outlook?
Grim. At the current rate, scientists predict there might be no glaciers left in Glacier National Park by 2030.
2030? That's incredibly soon.
It is. And this rapid loss of big ice masses, like the huge chunks breaking off Greenland and the Antarctic Peninsula, it's changing our understanding of how fast this can happen. The phrase glacial pace is kind of being redefined.
It's not slow anymore.
Not when it comes to these large-scale calving events. And this faster-than-expected delivery of ice into the ocean wasn't fully factored into some of the earlier IPCC projections.
Meaning sea level rise could be faster and higher than we thought.
It strongly suggests that, yes, the conservative estimates might be too conservative. We're likely looking at faster and potentially larger sea level rise this century.
Okay, all this evidence points towards significant change driven by warming, which leads to the idea of the Anthropocene.
Right, this proposed new geological epoch, the age of humans,
Yeah.
where we become the dominant force shaping the planet.
When did that start? Is there a date?
It's debated, but a common marker is the late 18th century. Think James Watt's improved steam engine, the beginning of the Industrial Revolution, and that's when atmospheric CO2 levels really started to take off.
Driven by our energy use.
Our immense energy use.
Yeah.
There's a striking analogy. Globally, our per capita energy consumption is like having 3.5 horsepower working constantly for every single person.
3.5 workhorses for everyone on Earth.
Yeah, imagine a global workforce of 25 billion phantom workhorses. And if you live in the U.S., it's much higher, about 15 workhorses per person.
That's a staggering amount of energy. And the main byproduct is CO2, this invisible gas.
Invisible, yeah. Which makes it easy to ignore. There's this thought experiment. What if carbon emissions weren't an invisible gas?
What if they were something else?
What if they came out as, say, ankle-deep horse manure, piling up everywhere we burn fossil fuels?
Okay, yeah. Attitudes might change pretty quickly then.
Drastically, you'd think.
Mm-hmm.
But because it is invisible, the consequences feel distant, abstract, until they become very real in specific places, like the Arctic.
Right. The melting ice there isn't abstract at all. It's opening up new realities.
Immediate geopolitical realities. Remember 2008, for the first time in recorded history, both the Northwest Passage over Canada and the Northeast Passage over Russia were open free of ice simultaneously.
Creating new shipping routes, access to resources.
Exactly. Suddenly, there's potential access to vast oil and gas reserves, new fishing grounds, and that's triggered a new kind of tension.
A scramble for the Arctic.
You see nations like Russia, Canada, the U.S., Denmark, Norway, all jockeying for position, making claims, especially over areas like the Lomonosov Ridge, thought to be rich in resources. The melting ice is redrawing the geopolitical map up there.
But moving from geopolitics to the direct human cost sea level rise, who pays the price first?
It's the people living in the lowest lying areas. Especially vulnerable are the coral atoll nations.
Tuvalu, Kiribati, the Maldives, places like that.
Precisely. For them, it's an existential threat. And it's not just about waves washing over the islands during storms.
Files.
The rising sea level actually pushes up through the porous coral rock and soil from below. It saturates the ground, contaminates freshwater supplies, kills agriculture, rendering the islands uninhabitable long before they're technically underwater.
So entire nations could simply cease to exist.
That's the stark reality they face. And the potential scale of displacement globally is enormous.
How many people are we talking about?
Globally, estimates suggest more than 100 million people live on land that's less than 3 feet, or about 1 meter above current sea level.
And a 3-foot rise is well within the range of projections for this century, right?
Easily within the range, yes. So if that happens, you could be looking at over 100 million climate refugees, people forced from their homes by the rising water.
100 million people. Think about the challenges we face with migration and refugees today. That scale.
It makes today's issues, as difficult as they are, look like a Sunday school picnic, as one source vividly put it. It's a humanitarian crisis potential on a scale we've never seen.
Which really forces us to think about the future. What can we even do now?
Well, that brings us to a sobering point. Because greenhouse gases, especially CO2, stay in the atmosphere for such a long time. CO2 lingers for over a century. Some amount of future warming is already baked in.
That's the climate commitment.
Exactly. Even if we stopped all emissions tomorrow, which is obviously not going to happen, the planet would continue to warm for some time due to the gases already up there.
So adaptation is no longer optional. We have to prepare.
We absolutely have to. Adaptation planning is essential. That means figuring out how to deal with the consequences. Higher peak electricity demand and heat waves, reinforcing or relocating infrastructure, planning for those potential mass movements of people, securing water resources. It's about managing the unavoidable.
And because the challenge is so huge, some people are now talking about more radical interventions, right? Climate engineering.
Yes, geoengineering. Deliberate, large-scale manipulation of the climate system. Ideas like spraying aerosols into the stratosphere to reflect sunlight, kind of planetary sunscreen, or fertilizing oceans to get plankton to soak up more CO2.
That sounds risky.
It's incredibly risky, and it raises a fundamental question we need to grapple with. How do we make sure the cure isn't worse than the disease?
History has some warnings there, doesn't it?
It certainly does. Think about CFC's chlorofluorocarbons.
The refrigerants used in air conditioners and spray cans.
Right. They were designed in the 1930s as a miracle solution. Non-toxic, non-flammable replacements for dangerous chemicals like ammonia. They seem perfectly safe, totally inert.
Until we discovered they were eating a hole in the ozone layer over Antarctica.
Exactly. A completely unforeseen, potentially catastrophic consequence decades later. It's a powerful reminder that when we intervene in complex planetary systems, unintended consequences are a real danger.
So as we consider drastic measures like geoengineering to fix the climate problem we created,
We have to be incredibly careful. We need to ask, could our solution inadvertently create an even bigger, perhaps completely unknown, problem down the line? It's a profound dilemma, forcing us to weigh the known risks of climate change against the unknown risks of attempting to engineer our way out of it. That's the unsettling thought to leave you with.